Hi there. The purpose of this video is to generate a shear force and bending moment diagrams for a loaded beam through Excel. So let's jump into the problem. We've got a loaded beam here, uniform distributed load of 150 newtons per meter, 15-meter long beam. You can see there's an overhang here. We've got two reactions here, R1 and R2. We've got two shear forces down the way, F1 and F2. So we know what F1 and F2 are, they are given values, but we don't know what R1 and R2 are. So how do we calculate them? So we calculate the reactions R1 and R2. If you've got two unknowns, you need two equations with the same two unknowns generated different ways. So the first way we're going to generate that is to look at the bending moments of this beam. So bending moments from a reference point is force times distance. And we can generate an equation for R2. The bending moment acts in the middle. We can generate an equation for R2. And if we know what F1 and F2 is, we can work out what R2 is. Then what we're going to do is we go back to our sum of the forces up and down. The beam is not moving, so it must be in equilibrium. We've got a formula for R1, which includes R2. If we know our R2, plug it into here, we can work out what R1 is. So again, we're in the 21st century. We're going to use Excel to do these calculations for us. And we're also going to use Excel to generate a shear force in the bending moment diagrams. So just a little bit of a background, shear force, fundamental concept in mechanics, so that we can understand loads on structures. Shear force is constructed from starting at one end of the beam and moving along its length. Then from that, we can create a bending moment diagram, which is the integral, which is the area under the shear force diagrams. So what bending moment is a rotational force. Uniform distributed load is linear across the beam. And here's a quick example of a shear force diagram. We've got a shear force here that is constant 2.5. The bending moment is adding the area under that curve. This is a constant. So out of a constant, if we integrate, we get an x power, because we add 1 to the exponent of x to the 0 here, because it's a constant. We get x to the 1, so we get a linear system. And here's another shear force, so the bending moment goes back down to 0 here. So bending moment is the integral of shear force. The rate of change of bending moment is shear force. So the rate of change here is linear, it's constant. That gives us 2.5. Our system is a UDL, so we're going to get this type of system here, where we've got a linear shear force diagram. And out of the linear shear force diagram, we're going to have an x squared type bending moment diagram, curve, parabolic. So let's jump into the Excel. We've already figured out our R1 and 2 reactions. So what we're going to do is create a shear force diagram. So what we've done here is every half meter resolution. So you need a reasonable resolution. So I've picked half meters so that we don't have enormous amounts of columns. So the shear force diagram starts here at the value of R1. So how do we accumulate going along? We've got 150 newtons per meter UDL. So if it's every half meter, then we subtract 75 as we go along from the previous cell up until the 5 meters. So what happens at 5 meters is we've got a shear force here. So we need to take account of the shear force at the same 5 meters, altering the shear force diagram because we've now got F1 coming down here. So if we select these, the horizontal dimension and the shear force for those particular values of F1 and F2, and we do, let's see, we want to do an insert and we want a scatter diagram, and we want smooth lines. No, we want straight lines. We want scatter diagram with straight lines, and we get our shear force diagram. So let's just make it bigger. Let's just make it bigger here. We've got a shear force diagram automatically generated out of our Excel. So what we've got here, we start at the value of R1 here, and then we've got a slope coming down here. It's linear. That slope is minus 150 from the UDL. So the slope here, the slope here, the slope here is all the same gradient because that's the UDL. These step changes here are the shear force of F1. Then we've got the reaction here, R2. Then we've got F2 coming down. And then the shear force diagram goes back to 0 as it must do. So how do we get the bending moment from this? We take the area under this curve, the area under the graph, and we can obviously see it goes, it's positive and negative. So if we do the bending moment diagram if we do the bending moment diagram numerically, so not using any rules of integral maths, what we're doing is we're chopping up the area under the graph into 0.5 meters steps, and we're taking the rectangular areas and then we're adding them all up and keeping a running total. So we start the bending moment at 0. The next one up here, so what are we doing here? We're actually taking the shear force, but we're actually taking the midpoint here. And we take the midpoint of linear so that if it's a linear system on the shear force, if we use the midpoint for the height of the rectangular area, we're actually going to get it accurate. Why is there 0.5 here? That's the width of the rectangular slice. So we're adding them all up, we're keeping a running total, and what's produced out of here is parabolic curves in 4 sections. If you look here, we've got section A to B, B to C, C to D, and D to E. And if we go back to our slides, that has come out of this diagram here. We've sectioned it out. Now, the reason we've sectioned it out there is what we're actually going to end up with is 4 sections where we're doing the integration, because the math formula for the integrals are going to be different, A to B, from B to C, from C to D, and from D to E. But the bending moment diagram should come back to 0 again. So if we do that, and then we'll just show how we got that. So we're selecting the X horizontal dimension. We've got our bending moments done numerical, not using any math formula. And what we're now going to do, we can get this up, if we're going to insert recommended charts. So let's say see all charts. Let's do XY scatter again. Let's choose the smooth one. No, let's smooth lines and markers. Now let's choose that one. And then we do OK. And we get our bending moment diagram. Now we can see our bending moment diagram is curved. It's an x squared function. It's not straight lines, it's parabolic. So we increase the bending moment through the first 0 to 5 meters. And then the bending moment goes very negative down here, and then gradually comes back up, goes back to 0 at 15 meters as it should do. Now we've got positive and we've got negative bending moments in here. So we can have some conclusions out of that we'll come to at the end. Let's do this again we've done this numerical integration where you don't need any rules of math. You're chopping up areas into small rectangular slices, but let's do it by integral maths. Using integral maths, we've got formulas for each of those sections, A to B, B to C, C to D, and D to E. We've got 4 integral equations. So how do we get these integral formulas? That is the equation for the first part of the section A to B. The minus 150x, minus 150 is the gradient, 612.5 is the starting point at R1. So for each section on the shear force diagram, each of those sections, A to B, B to C, C to D, and D to E, these lines have got different formulas. So if we integrate using mass, they're going to have different formulas as well. So it's essentially done in 4 sections. And then we keep a running total, and we can plot out the graph from using integral maths. And what happens is it's identical to our numerical. Now, the reason it's identical to the numerical, the math is the exact 100% accurate version of it, and numerical happens to be exactly the same because in the shear force diagram, we've got a linear slope here on the shear force. And if we take the midpoint, then we get it 100% accurate using numerical. If it wasn't linear and going up and down between the slices, then we wouldn't get the numerical to be accurate, but we would get it to be a very good approximation. So if we look at our bending moment diagram here, we can see that it's been auto-generated through Excel. We can see it's got 4 sections. They're all x-squared functions, but they've got different formulas. And we can have some conclusions by looking at those graphs if you were to explain them, particularly to a non-technical person. So bending moment diagram is the area under the shear force diagram. Bending moment sum to 0 at the end of the beam. The bending moment has peaks when the shear force crosses the 0 axis. When bending moment is positive, the beam is sagging. When the bending moment is negative, the beam is hogging, so it's going the opposite way. In this particular case, because we've got a linear shear force diagram, the results for numerical and analytical using math integral formulas turn out to be exactly the same. And just to point out on the bending moment diagram is not exponential, it's a parabola, because we have an x-squared function, x being the length of the beam going from 0 to 15, so it's curved. Thank you for watching, and that shows how we can generate shear force and bending moment diagrams from Excel. So we go back up to here. We go back up to here. Stop sharing.